how to fuse this information temporally. So we looked at three-dimensional convolutions, transformers, axial transformers in an effort to try to make them more efficient, recurrent neural networks of a large number of flavors. But the one that we actually like quite a bit as well, and I want to spend some time on, is a spatial recurrent neural network video module. And so what we're doing here is, because of the structure of the problem, we're driving on two-dimensional surfaces, we can actually organize the hidden state into a two-dimensional lattice. And then as the car is driving around, we update only the parts that are near the car and where the car has visibility. So as the car is driving around, we are using the kinematics to integrate the position of the car in the hidden features grid. And we are only updating the RNN at the points where we have that are nearby us, sort of. So here's an example of what that looks like. Here, what I'm going to show you is the car driving around, and we're looking at the hidden state of this RNN. And these are different channels in the hidden state. So you can see that this is after optimization and training this neural net. You can see that some of the channels are keeping track of different aspects of the road, like, for example, the centers of the road, the edges, the lines, the road surface, and so on. Here's another cool video of this. So this is looking at the mean of the first 10 channels in the hidden state for different traversals of different intersections. And all I want you to see basically is that there's cool activity as the recurrent neural network is keeping track of what's happening at any point in time. And you can imagine that we've now given the power to the neural network to actually selectively read and write to this memory. So for example, if there's a car right next to us and is occluding some parts of the road, then now the network has the ability to not write to those locations. But when the car goes away and we have a really good view, then the recurrent neural net can say, OK, we have very clear visibility. We definitely want to write information about what's in that part of space. Here's a few predictions that show what this looks like. So here we are making predictions about the road boundaries in red, intersection areas in blue, road centers, and so on. So we're only showing a few of the predictions here just to keep the visualization clean. And yeah, this is done by the spatial RNN. And this is only showing a single clip, a single traversal, but you can imagine there could be multiple trips through here. And basically a number of cars, a number of clips could be collaborating to build this map, basically and effectively an HD map, except it's not in a space of explicit items. It's in a space of features of a recurrent neural network, which is kind of cool. I haven't seen that before. The video networks also improved our object detection quite a bit. So in this example, I want to show you a case where there are two cars over there, and one car is going to drive by and occlude them briefly. So look at what's happening with the single frame and the video predictions as the cars pass in front of us. Yeah, so that makes a lot of sense. So a quick playthrough through what's happening. When both of them are in view, the predictions are roughly equivalent. And you are seeing multiple orange boxes because they're coming from different cameras. When they are occluded, the single frame networks drop the detection, but the video module remembers it, and we can persist the cars. And then when they are only partially occluded, the single frame network is forced to make its best guess about what it's seeing, and it's forced to make a prediction, and it makes a really terrible prediction. But the video module knows that there's only a partial, it has the information, and knows that this is not a very easily visible part right now, and doesn't actually take that into account. We also saw significant improvements in our ability to estimate depth, and of course, especially velocity. So here I'm showing a clip from our remove the radar push, where we are seeing the radar depth and velocity in green, and we were trying to match or even surpass, of course, the signal just from video networks alone. And what you're seeing here is in orange, we are seeing a single frame performance, and in blue, we are seeing, again, video modules. And so you see that the quality of depth is much higher. And for velocity, the orange signal, of course, you can't get velocity out of a single frame network. So we just differentiate depth to get that. But the video module actually is basically right on top of the radar signal. And so we found that this worked extremely well for us. So here's putting everything together. This is what our architecture roughly looks like today. So we have raw images feeding on the bottom. They go through a rectification layer to correct for camera calibration and put everything into a common virtual camera. We pass them through RegNets, residual networks, to process them into a number of features at different scales. We fuse the multi-scale information with BiFBN. This goes through a transformer module to re-represent it into the vector space in the output space. This feeds into a feature queue in time or space that gets processed by a video module, like the spatial RNN. and then continues into the branching structure of the HydraNet with trunks and heads for all the different tasks. And so that's the architecture roughly what it looks like today. And on the right, you are seeing some of its predictions sort of visualized both in a top-down vector space and also in images. So definitely, this architecture has definitely complexified from just a very simple image-based single network about 3 or 4 years ago and continues to evolve. It's definitely quite impressive now. There's still opportunities for improvements that the team is actively working on. For example, you'll notice that our fusion of time and space is fairly late in neural network terms. So maybe we can actually do earlier fusion of space or time and do, for example, cost volumes or optical flow-like networks on the bottom. Or for example, our outputs are dense rasters, and it's actually pretty expensive to post-process some of these dense rasters in the car. And of course, we are under very strict latency requirements, so this is not ideal. We actually are looking into all kinds of ways of predicting just the sparse structure of the road, maybe like point by point, or in some other fashion that doesn't require expensive post-processing. But this basically is how you achieve a very nice vector space. And now I believe Ashok is going to talk about how we can run plane and control on top of it.
Thank you, Andre. Hi, everyone. My name is Ashok. I lead the planning and controls, auto labeling, and simulation teams. So, like Andre mentioned, the vision networks take dense video data and then compress it down into a 3D vector space. The role of the planner now is to consume this vector space and get the car to the destination while maximizing the safety, comfort, and the efficiency of the car. Even back in 2019, our planner was a pretty capable driver. It was able to stay in the lanes, make lane changes as necessary, and take exits of the highway. But city driving is much more complicated. Rarely there are structured lane lines. Vehicles do much more free-form driving than the car has to respond to all of cut-ins and crossing vehicles and pedestrians doing funny things. What is the key problem in planning? Number one, the action space is very non-convex. And number two, it is high-dimensional. What I mean by non-convex is there can be multiple possible solutions that can be independently good, but getting a globally consistent solution is pretty tricky. So there can be pockets of local minima that the planning can get stuck into. And secondly, the high dimensionality comes because the car needs to plan for the next 10 to 15 seconds. It needs to produce the position, velocities, and acceleration over this entire window. This is a lot of parameters to produce at runtime. Discrete search methods are really great at solving non-convex problems because they are discrete, they don't get stuck in local minima, whereas continuous function optimization can easily get stuck in local minima and produce poor solutions that are not great. On the other hand, for high-dimensional problems, discrete search sucks because it is discrete, it does not use any graded information, so literally it has to go and export each point to know how good it is. Whereas continuous optimization uses gradient-based methods to very quickly go to a good solution. Our solution to this entire problem is to break it down hierarchically. First, use a code search method to crunch down the non-convexity and come up with a convex corridor, and then use continuous optimization techniques to make the final smooth trajectory. Let's see an example of how the search operates. So here, we're trying to do a lane change. In this case, the car needs to do 2 back-to-back lane changes to make the left turn up ahead. For this, the car searches over different maneuvers. So in the first one it searches is lane change that's close by, but the car brakes pretty harshly, so it's pretty uncomfortable. The next maneuver it tries does the lane change a bit late, so it speeds up, goes in front of the other cars, and finally does the lane change. But now it risks missing the left turn. We do thousands of such searches in a very short time span. Because these are all physics-based models, these futures are very easy to simulate, and in the end, we have a set of candidates, and we finally choose one based on the optimality conditions of safety, comfort, and easily making the turn. So now the car has chosen this path, and you can see that as the car executes this trajectory, it pretty much matches what we had planned. The cyan plot on the right side here, that one is the actual velocity of the car, and the white line underneath it was the plan. So we are able to plan for 10 seconds here and able to match that when we see in hindsight. So this is a well-made plan. When driving alongside other agents, it's important to not just plan for ourselves, but instead we have to plan for everyone jointly and optimize for the overall scene's traffic flow. In order to do this, what we do is we literally run the autopilot planner on every single relevant object in the scene. Here's an example of why that's necessary. This is an auto corridor. I'll let you watch the video for a second. Yeah, that was autopilot driving in an auto corridor, going around parked cars, cones, and poles. Here, there's a 3D view of the same thing. The oncoming car arrives now, and autopilot slows down a little bit, but then realizes that we cannot yield to them because we don't have any space to our side. But the other car can yield to us instead. So instead of just blindly braking here, autopilot reasons about that car has low enough velocity that they can pull over and should yield to us because we cannot yield to them, and assertively makes progress. A second oncoming car arrives now. This vehicle has higher velocity, and like I said earlier, we literally run the autopilot planner for the other object. So in this case, we run the planner for them. That object's plan now goes around their side's parked cars, and then after they pass the parked cars, goes back to the right side of the road for them. Since we don't know what's in the mind of the driver, we actually have multiple possible futures for this car. Here, one future is shown in red, the other one is shown in green. The green one is a plan that yields to us. But since this object's velocity and acceleration are pretty high, we don't think that this person is going to yield to us, and they are actually going to go around these parked cars. So autopilot decides that, OK, I have space here. This person is definitely going to come, so I'm going to pull over. So as autopilot is pulling over, we notice that that car has chosen to yield to us based on their yaw rate and their acceleration. And autopilot immediately changes its mind and continues to make progress. This is why we need to plan for everyone, because otherwise we wouldn't know that this person is going to go around the other parked cars and come back to their side. If we didn't do this, autopilot would be too timid and would not be a practical self-driving car. So now we saw how the search and planning for other people set up a convex valley. Finally, we do a continuous optimization to produce the final trajectory that the planner needs to take. Here, the gray thing is the convex corridor. And we initialize a spline in heading and acceleration, parameterized over the arc length of the plan. And you can see that the optimization continuously makes fine-grained changes to reduce all of its costs. Some of the costs, for example, are distance from obstacles, traversal time, and comfort. For comfort, you can see that the lateral acceleration plots on the right have nice trapezoidal shapes. It's going to come up for, yeah, here on the right side, the green plot has a nice trapezoidal shape. And if you record a human trajectory, this is pretty much how it would look like. The lateral jerk is also minimized. So in summary, we do a search for both us and everyone else in the scene. We set up a convex corridor and then optimize for a smooth path. Together, these can do some really neat things like shown above. But driving looks a bit different in other places, like where I grew up from. It's very much more unstructured. Cars and pedestrians cutting each other, harsh braking, honking. It's a crazy world. We can try to scale up these methods, but it's going to be really difficult to efficiently solve this at runtime. What we instead want to do is use learning-based methods to efficiently solve them. And I want to show why this is true. So we're going to go from this complicated problem to a much simpler toy parking problem, but still illustrates the core of the issue. Here, this is a parking lot. The Ego car is in blue, and it needs to park in the green parking spot here. So it needs to go around the curbs, the parked cars, and the cones shown in orange here. So it is a simple baseline. It's a A-star, it's a standard algorithm that uses a lattice-based search. And the heuristic here is the distance, the Euclidean distance to the goal. So you can see that it directly shoots towards the goal, but very quickly gets trapped in a local minima. And it backtracks from there, and then searches a different path to try to go around this parked car. Eventually, it makes progress and gets to the goal, but it ends up using 400,000 nodes for making this. Obviously, this is a terrible heuristic. We want to do better than this. So if we added a navigation route to it and has the car to follow the navigation route while being close to the goal, this is what happens. The navigation route helps immediately, but still, when it encounters cones or other obstacles, it basically does the same thing as before, backtracks and then searches a whole new path. And this poor search has no idea that these obstacles exist. It literally has to go there, check if it's in collision, and if it's in collision, back up. The navigation heuristic helped, but still this took 22,000 nodes. We can design more and more of these heuristics to help the search go faster and faster, but it's really tedious and hard to design a globally optimal heuristic. Even if you had a distance function from the cones that guided the search, this would only be effective for the single cone, but what we need is a global value function. So instead, what we want to use is neural networks to give this heuristic for us. The vision networks produce a vector space, and we have cars moving around in it. This basically looks like an Atari game, and it's a multiplayer version. So we can use techniques such as mu0, alpha0, et cetera, that was used to solve Go and other Atari games to solve the same problem. So we're working on neural networks that can produce